Today I'm going to talk about a couple of really important ideas that have to do with the data displays we've been discussing in class, but I want to make sure we've got accurate background knowledge established first. And I'm going to use the following situation in order to be able to talk about that background information. It says Robert can download 2 songs from the internet each minute. This is shown on the table and in the graph. So at 0 minutes, obviously, he's downloaded 0 songs. At 1 minute, he's downloaded 2. At 2 minutes, he's downloaded 4. At 3 minutes, he's downloaded 6. At 4 minutes, he's downloaded 8. So all that information is on a chart. I am going to take that information and put it into a scatter plot. And I've created for myself an X and Y axis. I'm going pretty quickly on this because I'm assuming this is all background knowledge. As you'll recall from class, the independent variable, the one that kind of affects the other one, goes on the X-axis across the bottom. And then the dependent variable, the one that depends on the other, goes along the Y-axis. In almost 100% of times, the time involved in the situation is going to be your independent variable, and the other item is going to be the variable that depends on how much time you have. Makes pretty good sense. The more time you have, obviously, the more you'll be able to have something occur. The less time you have, the less frequently something will be able to occur. So almost always, time is going to be your independent variable, and there is no exception here. The more time you have to download stuff, the more songs you're going to download. So we are going to, I've set up a scale here, just goes from 0 to 4, just like my time on my graph, from 0 to 8, just like my number of songs. And then I'm going to graph my dots on my scatter plot. So I've got a 0, 0 to represent the fact that at 0 time, we've downloaded 0 songs. At 1 minute, we've downloaded 2, so I'm going to go over to 1 minute, up 2 to represent the fact that at 1 minute, I've downloaded 2 songs. At 2 minutes, we've downloaded 4 songs, so I'm going to place the coordinate in the appropriate spot. At 3 minutes, we've downloaded 6 songs. And at 4 minutes, we've downloaded 8 songs. Now, it's also important to note, you guys have actually seen scatter plots, or you've seen graphs before where the dots are actually connected in between the dots, and it actually looks more like a line graph. Let me explain to you why I'm not going to do that this time. Now, I could probably assume, now the question should give us a little bit more information, but it says that Robert can download 2 songs from the internet each minute. Now, that leads me to believe, probably, that if I can download 2 songs in 1 minute, then I can probably download 1 song in a half of a minute. So more than likely, there's probably another data point, set of data points that should be around here. Like at half of a minute, I can download 1 song. At 1.5 minutes, I can download 3. At 2.5, I can download 5, etc. Because it makes sense that now the question doesn't give us this information. I'm only making an inference, and there could be something that causes this to not be true. But we can probably infer that every half of a minute we can download 1 song, which is what I'm showing you here. So at 1 minute, I've got 2. At 1.5 minutes, I've downloaded 3, etc. Because the question did not explicitly tell us that, though, maybe there's something weird about his computer so that, that's not the case. I'm going to go ahead and just stick with my original data points for now. Now, the reason that I cannot connect the dots, even after I added that other set of data in, is because when you are connecting the dots, you are basically saying that all of the pieces of data that fall along this line are possibilities for data that go along with this particular data set. For example, and let me get a different color here. So, for example, because it's sitting on the line right here, oh, well, that didn't work into a different color, but that's okay. Because this data point is sitting on the line right there, that means that after a half of a minute, I've downloaded 1.5 songs. Okay, now, or actually, let me line this up a little bit better here. if I line it up a little bit better, let's see here. It's actually going to be about here. So this is about 1.5 songs right here. So according to, if I leave the dots connected, if I look at this little spot right here, this is saying that a little bit less than a minute, I could have about 1.5 songs downloaded, because right here is about where 1.5 would be. And so by virtue of the fact that that line is here, it's saying that any of these places in between are possibilities. Here's another example right here. If I leave the line included right here, it's saying that it's possible to actually have 3.5 songs downloaded. Now, anybody that's ever downloaded songs before knows that you can't download and walk around with 3.5 songs. You can't have a half of a song downloaded. So if I connect the dots here, the fact that there is a place on the graph graphed in these areas right here, like that fall in between the number of songs, that's actually saying that you could have half of a song, and we know that that's not the case. So we are not going to connect the dots. I'm going to take a second and kind of clean this graph up a little bit. All right, so that's better. So just as a reminder, I don't have any lines connecting the dots because a data point located in between would indicate that I could have, for example, right here, 3.5 songs, which we know is not the case. So that's why we're sticking to a scatter plot. Now that we've got all that background information worked out, let's talk about some of our new information. So there is something that we call a rate of change. And rate of change is determined by looking at what's going on in between two data points. It could be any two data points. So I'm just going to look at these two right here for right now. And when we say rate of change, we mean at what rate did the two variables change as we move from this data point to this data point. And there's really just a simple matter of counting, kind of like a transformation. Okay, so to go from this point to this point, we recall from when we did transformations, so we have to move over to the right one place, then we have to go up 2 places. So we hop from here to here over to the right one, then we hop up 2. So we move over to the right one, we move up 2. Positive 1, positive 2. We remember from our transformations unit, a shift to the right is positive, a shift up is also positive. Now, rate of change is when you actually put into numerical form a way to describe how it changes from here to here. So every single time this moves over 1, this one moves up 2. So your rate of change would say, every single time I go up 2 songs, I go over to the right, and it increases by 1 minute. So the change is an increase of 2 songs. The increase is demonstrated by the fact that that's a positive 2. And every time there is an increase of 2 songs, there is an increase of 1 minute. Again, the increase is demonstrated by the fact that this is a positive 1. If it had been a negative 1, that would indicate that it goes down 1 minute. So every single time the number of songs increases by 2, the minute increases by 1. Now, a lot of people are probably sitting at home right now saying, why does the number of songs go on top? Because we have hammered into your heads for years now that when you're graphing stuff, you address left to right first, then you address up and down second. So I can see why it would be totally confusing that you put the change over, that you take the vertical change and it goes on top, and you take the horizontal change and it goes on the bottom. It just doesn't seem to make any sense that the change is songs over time instead of time over songs. Seems like it should be 1/2 as a rate of change instead of 2 over 1. Well, let me give you another example. And I'm going to introduce a word to you that I know you've heard before outside of math class, but that you probably haven't talked about a whole lot inside of math class, and that is the term slope. Like when we talk about the slope of a hill, like when you go skiing, for example. Okay, the steeper the hill, okay, let's say this, we're going skiing, we're going uphill skiing. So here's a mountain here, and then here's another mountain here. Well, which one is more steep? Okay, well obviously it's going to be this one because it slopes upwards at a much harder rate. This is one that's a lot more steep. Same thing if we've got a downward slope. Okay, this one is going to be a lot more steep than this one that's kind of more of a gentle way because it's a lot more steep. Okay, the more steep it is, the higher the number is going to be. Okay, the higher the slope. Okay, so let me graph a couple lines for you really quickly here. So if you were skiing, you would look at these two mountains that are graphed on the graph, and you would say, oh, well this one is definitely more steep than the other one, clearly, which means that the number that represents its slope should be bigger than the number that represents this slope right here. Okay, if it's more steep, that means it's going to have a bigger slope. Okay, that just makes common sense. So this one is less steep, which means its slope is going to be smaller. So let's see why you actually do the vertical change over the horizontal change when you're figuring out the steepness of the slope. Or what we call it when we're talking about the real world, the rate of change. It's just another word for the slope of the line. So let's count here. So to go from this data point to this data point, we're going to hop up 2. We're going to go over 1. We're going to hop up 2. We're going to go over 1. Okay, and that's actually going to be the case for every single one of these. Okay, that means that the slope is, if we do the vertical change over the horizontal change, so the up and down change is 2, so it goes on top. The horizontal change is 1, so the slope is 2 over 1. Okay, if we just did it correctly, that means that this slope of this line right here should be bigger than the slope of the line right here. So let's see if that's the case. So I'm just going to count from this point to this point. You hop up 1, and then you hop to the right 2. You hop up 1 over to the right 2. So the slope for this one is actually, if we do our up and down change first, then our left to right change second, that means it's going to be 1/2. Because you go up 1, then you go over 2. Well, it makes perfect sense. This slope is 2 over 1, and it's a lot more steep, whereas this one is 1/2. It's a lot less steep. So we know that that works. Okay, let's do it the wrong way for a second. Let's just assume, again, I'm emphasizing I'm doing this the wrong way. Okay, common sense tells us this is more steep. That means it's going to have the bigger slope. So let's say I have a brain cramp moment. I do my horizontal change. Okay, I do my left to right change first, then my vertical second, because I mess up and I do it backwards. So it goes over to the right 1, which is a positive 1, then it goes up 2. Okay, that means that the slope of this line is 1/2. Then I say, all right, this one goes to the right 2, and then it goes up 1, which makes it a positive 2 over 1. Okay, so something should be telling us, as far as common sense, that, this one's actually more steep, but then yet its slope is smaller than its slope here. Okay, so that should tell you that something is wrong. Okay, it's really kind of hard to remember. Again, we have totally hammered into your heads that you need to do your left to right change first and then your up and down second, but that's not the way that it works. You write down how much it changes up and down first on top, then you write down how much it changes left to right second. There's actually a little expression that when you get to Algebra 1, you will hear all the time. It's called rise over run. That means you do the vertical change first, put it on top of the horizontal change. So this little expression, rise over run, will help you to remember that. Okay, so remember that our rate of change is just another way of saying the slope of the line that's going on here. So if we go back to our other example, so this one went to the right 1, and then it went up 2. Okay, same thing here. It went up 2. Then it went over 1. It went up 2. and it went over 1. So our rate of change in between every single data point was actually the same. It had, there's another word for this, when your change from one data point to the other is exactly the same. It's still called a rate of change, but then it's called a constant rate of change, which definitely makes sense. If it's a constant rate of change, that just means that your rate of change in between each of your data points stays the same constantly. And I wonder if we notice something else. So this is an example of where we have a constant rate of change. And look at the formation of the coordinates on the scatter plot. And you notice they look really straight. I wonder if that happens for every single occasion where we have a constant rate of change. Maybe we should look at another one. So here's another table of information that represents, apparently it looks like somebody's bank balance in their account based on the number of transactions that they've had. So after 3 transactions, a transaction means you either take out or put in money. So after 3 transactions, their balance was 170. But then after 6 transactions, it's 140. After 9, 110. So it looks like the transaction they must be doing is withdrawing money. Because as your number of transactions goes up, your balance is going down. So I put my number of transactions on my x-axis because that is my independent variable. The amount of money that's in your account is going to depend on how many transactions you do. I've already graphed the data. I'm not going to rehash how I did that. Let's take a look at our rate of change. So remember our rise over run, which is just another way of saying what the slope is, which is just another way of saying rate of change. Okay, so we talked about all these different meanings of these terms. So to go from this data point to this data point, we went down from 170 down to 140. So we decreased by $30. Then we hopped over 3 units. Be careful about your scaling. What a lot of people would have done is just counted down 1, 2, 3 instead of counting down 10, 20, and 30 like we did here. So be careful and make sure that you don't miscount. So our vertical change here is 30. Our horizontal change, our left to right change, is 3. Okay, let's see if it holds true for everything else. So to go from here to here, again we went down 10, 20, 30. And then we increased by 3. Oh, sorry, I goofed and I should have put a negative in front of this 30 because it's going down 30. So that's a negative 30. Then I went down 10, 20, 30 again. Went to the right 3. So I have the same rate of change for every change in between every data point. It goes down 30 and it increases by 3. Okay, our balance decreases by 30. Our number of transactions increases by 3. Because it's the same, you'll recall from our discussion a moment ago, that this is called a constant rate of change. So because we have a constant rate of change, let's look at the shape. And just like the one that we had a moment ago, where it formed a straight, where they all formed a perfectly straight line, look, again, they also form a perfectly straight line. And I'll just go ahead and tell you that this happens every single time your data has a constant rate of change in between each of them. Okay, so whenever the rate of change is constant between each one, it forms a straight line, and there's a special word for that also, which is linear. Has that word line in there, which should give you a clue that linear means that it forms a straight line. And this happens every single time you have a constant rate of change. Again, that rate of change is based on your up and down difference over your left to right difference. The way we say that is rise over run, which is also called the slope. So here's another example of where we have a chart that shows the relationship between Celsius and Fahrenheit. There's actually a relationship, a formula you can use between the two. And when it's 0 degrees Celsius, it's actually 32 degrees Fahrenheit. When it's 9 degrees Celsius, it's 37 degrees Fahrenheit. When it's 18 degrees Celsius, it's 42 degrees Fahrenheit. So I've graphed that relationship. This is one of those cases where it really wouldn't have mattered which one I put on the X and the Y axis, because it's not like the Celsius temperature causes the Fahrenheit temperature or vice versa. So this was really just an arbitrary decision that I put the Celsius on the X and that I put the Fahrenheit on the Y. There really wasn't any special reason that I did either one of those. And I'm also going to connect my dots in between my scatter plot points. And the reason for that is because I can actually have, for example, this little data point right in between here shows 39.5 degrees. Well, you can have 39.5 degrees. It's on the news all the time. You know that you can have a decimal of a degree. So whereas in our previous example where we were doing number of transactions, you can't go to the bank and do 1.5 transactions. So I did not connect the dots in between my point. Now I did here just to show that they form a straight line, but as far as actually connecting the dots for the graph, I did not do that. So, but here, however, I can connect my dots because you can have half of a degree. So I'm representing that idea by saying that in between each of these data points, all these data points is a possibility. So now let's look at our rate of change. It would probably be a good idea if you actually pause the video right now and try to look at the rate of change yourself and figure out what it is. I'm going to go ahead and keep working it though. So I'm looking at the change in between two data points, and in this case it went up from here to here. It went up 1, 2, 3, 4, 5 degrees, and it moved horizontally. Pay attention to my scale. It did move over 3 because I actually counted by 3s along my scale. So it went over 3, 6, 9 degrees. So the horizontal change was a positive 9. The vertical change was a positive 5. Remember that we do rise over run. So my rate of change is going to be 5 over 9. Remember, another way of saying the rate of change is the slope of the line, just like the slope of your ski resort mountain you're going up. Okay, and you'll see that it's actually the same from here to here. If we count, we go up 9, and then we go over 3, 6, if we count up, we go 5 up, and then we count over 3, 6, 9. So again, the rate of change stays the same, which means that this is a constant rate of change, which also makes this what? If it has a constant rate of change, hopefully you said it at home, that also makes it linear, which means that if you line up the data points together, they work out to form a straight line. So whenever you have a constant rate of change, that's going to result in the data being linear as well. Just thought I'd show you one more quick example of one that is not linear. Now you'll notice in this example it says this is the relationship between what day of the month it is and how much money is in your account. Now you'll notice that when they graphed this, they did connect the dots because you can have a half of a day and you can have a fraction of a dollar. That's what cents are for. You can do that. So in this case, apparently, now some banks do it differently where they don't determine your balance until the end of the day, but apparently when they decided to make up this data, they're saying that yes, you can throughout the day determine how your balance changes. So the dots are connected because you can have a decimal of a dollar, that's what cents are, and you can have a fraction of a day. So you'll notice here though, if we count, and they've marked the rate of change for us, but it might be a little hard for you to see at home, so I'm going to kind of highlight it here. So it went down $265 from here to here, and it went over 5 days. They highlighted it right there and right there. You might not be able to see that. So your balance decreased $75, which is a negative 75, and then the days increased by 5. That means 5 days went by. So the rate of change here is negative 75 over 5. But then you'll notice that from this data point to this data point, it only went down, it went down by a smaller amount, and the horizontal change was 10. So it's pretty obvious that your rate of change is not constant because it's not going down and over by the same amount every time. And then it should be extremely obvious to you that consequently, because this doesn't have a constant rate of change, the data is not linear. So just wanted to show you an example of some data that is not linear as well. And what's going to make the difference is whether or not it has a constant rate of change. Now, remember that you really don't have to graph the stuff every single time to figure out whether it has a constant rate of change. You don't have to graph it and count it. In this chart, for example, because gosh, that's a lot of work. What you really could do is just look at your differences in your y values, because that's really all you're doing when you're counting your vertical change. You're just seeing what your old value, what your old y value used to be, in this case 32, and what it changed to, which in this case is a 37. Okay, so you're really just looking at how the y value changed versus how the x value changed. So to find the rate of change, you really don't have to go through, now you're more than welcome to go through the trouble of graphing this if you want to, but you don't have to graph it all. So if I look here at the difference in my rate of change, for example, so if I were graphing that, I could graph it, and I could say that my days are on my x-axis, my balance is on my y, there's day 1, day 2, day 3, etc. So I could say it went over 1 and then up 550. And then on day 6, 4, 5, 6, I'm just going to do a really just lousy kind of sketch here. It was only at 285. Well, so then you would do 550 minus 285 to figure out how much it changed. So if you did that, because it went down, and if you did that, you would see that it's 265, that it went down from this data point to this data point. Then to count from 1 day to 6 days, it went over 5. So the rate of change is 265, and more specific, negative 265 over 5, because the balance decreased by 265, the day increased by 5. But you can accomplish the same thing without graphing it, just by subtracting here your difference. 550 minus 285 is 265. 6 minus 1 means it went up 5. So, or actually, you should do 285 minus 550, and you get your negative 265. So your rate of change, look at that, 265. Okay, to get your rate of change here, do your 210 minus 285. You'll see it went down by 75. Here it went from 6 to 16, so it increased by 10. Well, my change in my y values was negative 75. My change in my x values was 10, so the rate of change there was negative 75 over 10. So you don't have to go through the process of graphing. You can just look at the chart and figure it out that way. Here, our y change, 210 minus 210 is 0. Okay, so it didn't change vertically at all. 22 minus 16 means it increased by 6 days. So the rate of change here would be 0 over 6. So if you're given the information in a chart, you can definitely graph it this way, but you do not have to. Sometimes it's easier just to subtract.